In any study of differential equations, I think it's important to have a motivating example, preferably more than one, but we'll start with one common one, which is going to turn out to be surprisingly rich. And the idea is relatively simple. We're going to look at a mass that's attached to a spring that is attached to a wall. So the wall is fixed, but the mass can oscillate back and forth depending on how stretched or compressed the spring is. If we track x as being the position of this edge of the block where the spring meets the block, that's one way to define it. And if we define x equals 0 as the equilibrium point for the spring, or equilibrium location for the spring, then how would we describe x in words? Well, what we're talking about is imagining any possible scenario where we stretch the spring out, maybe give it a nudge, and then let it go. Just let it oscillate afterwards. And x of t in that case would be a prediction. And I cannot emphasize this enough. A lot of engineering students treat differential equations, especially early on, and fair enough, as this mathematical thing you just do. But at the heart and soul, when you look at someone who's modeling how a plane wing works, how a network is going to work under stress, if it's a differential equation that's being used for the modeling, you are building a prediction about what the system's going to do in the future, knowing what you know about the underlying physics. So here, specifically, it's a prediction of the position of the mass over time. So without actually building the system, without actually having to witness it in action, we think, knowing Newton's laws, that we can predict what the spring system is going to do in the future if we know a few things about the system itself. Well, how are we going to make that kind of prediction? Well, we're going to use our physics. So we've got our slab here, we've got our mass, and let's just rhyme through some of the free body diagram issues. Of course we have gravity, but in this particular scenario, we're not that interested in gravity because in the vertical direction anyway, there's going to be a perfectly balancing force there for the normal force. Other than that, the only force that's going to be applied is going to be the spring force. There might be friction, but we're not going to include that yet. We'll bring it in a little bit later. But in the horizontal direction, without friction, the only force acting on this mass is the spring force. And, I should add a little vector there, though we're just going to be working in one dimension, so it's not super crucial. The spring force magnitude is k times x, where k is the spring force in newtons per meter. And why is it newtons per meter? Well, because we're multiplying it by x, which is the displacement from equilibrium for the spring. So if I'm displaced by 0.01 meters, I'm going to multiply that by some spring constant, 5 newtons per meter. That's going to give me a Newton force for the spring. Now the extra ingredient that we're going to need as well is a negative sign in front here. And that simply comes from looking at scenarios. If x is positive, that would imply the spring is stretched. And if the spring is stretched, then the spring pulls back. And let's add some directionality here. I think that'll make it a little more clear. If the string is stretched to the right away from the wall, then the spring will pull to the left. And likewise, if x is negative, then the spring is compressed against the wall, and the spring will push to the right. And the lovely thing about this mathematical form is it takes care of both of those without you having to think about it. If x is negative, we multiply by negative and we get a positive spring force. If we've moved to the left, the spring pushes back to the right. And then if x is positive, it's more clear. If x is positive, we get a negative force. So if we've moved the spring to the right, the spring resists that and pulls to the left. So let's build our intuition a little bit about this, just working with the basic mechanics. If we have a spring, and if we say it's very stiff, think about what that means for you for a moment. So a very stiff spring, like a car spring, versus maybe one you've seen in the lab. The car spring would typically be something stiffer. Take a moment to think, then we'll check in. Okay. Hopefully you picked large, absolutely. Because if we take a look at our force equation, our force is equal to negative k times x, and stiff implies that for a small x, we get a big force. Even if you just move a little bit, if you try to push on a stiff spring, it's really, really hard. Well, it's really, really hard because the force is large, and so that means we must have a large scalar factor in between our displacement and the force. And I should say even for small x's. If you try to do large x's, it's even more force, but a stiff spring, usually we can't move it that much because it is so hard to push, and that's because it has such a large k value. Now, what if we trade a soft spring? So again, think something you might find in a physics lab, and we swap that out and we replace it with a car spring, car suspension spring. What do you think is going to happen to the period of the oscillations? And try to imagine, again, you got this mass. It was oscillating before, back and forth, back and forth, back and forth, back and forth. And then you swap out a soft spring for a stiff spring. What's your intuition tell you about what will happen to the period, how long it takes to complete one back and forth cycle? Take a moment, then we'll check in. Okay. Hopefully here you said the period will be shorter. And as a quick why for a rationale here, again, if we just think of our mass in the two scenarios, in both cases, if we have a soft spring versus a stiff spring, what changes between those two? Well, here we have a small force, say the displacement centered around here. We have a small f, or smaller f, and this gives us a larger f for the spring because stiffer springs have larger coefficients. That means for the same displacement, we get a larger force. And if you're going to have a larger force, you're going to be moving back towards the center at a faster rate because the larger force leads to larger acceleration. And so you're going to shoot through, say, 0 more quickly than you would have under these more relaxed spring conditions here. And the faster you get through 0, the faster you're going to end up reaching your far point and then back and completing one full cycle. So the stiff spring will lead to a shorter period for one cycle. Okay, so soft versus stiff springs. What about masses? If we take a small mass and replace it with a heavier mass, what do we think is going to happen to the period again? So this time the spring is constant. We're just going to change this mass that we have. And again, if it helps, think of it as a small mass, and then think of it as a large mass. And what the impact of that will be on the oscillation period. Take a moment and we'll check in. Okay, hopefully you went for that one. For a very similar rationale to the last one, except we focus on something different. In both of these cases, the force is the same. So in both of these, whatever force we have comes from the spring, but the force doesn't depend on our mass, it's just the stretching. But the acceleration here, because we take acceleration is force divided by mass, F over m is going to be larger. So the acceleration we get for this particular scenario is going to be larger, whereas with a big mass, we're going to get a relatively small acceleration from the same force. You know, it has more inertia, whatever mental model you use for this. Big heavy mass, harder to get moving, and that means there's less acceleration for the same force, so it's going to dawdle its way in towards the center, whereas this light mass is going to be more responsive. It's going to jump around more easily because it has less inertia. So if we increase the mass, we're going to have longer periods. It's going to take longer to complete one full cycle. Okay, so where does this leave us? Well, conceptually, if we know what the spring constant K is, and we know what the mass of the block is, and we assume friction is not in play here, should we be able to determine the exact period, like in seconds? How many seconds will it take this mass with a 5 Newton per meter spring and a 2 kilogram mass? Should we be able to determine the exact period? I'm like, well, if we can't, then why are we doing physics, right? Yes, absolutely. In the system, from the way we've analyzed it, there is nothing else to know besides the spring constant and the mass. They're the only things in play. And so we absolutely should be able to predict the period. Now the question is, do you know someone who knows the period? Again, we've talked about the influence of K and M on the period, but we should be able to get it, but how do we get it? And if someone pops out the answer, you can Google it if you like, you're going to get yourself a period equal to 2 pi square root of M over K. And if you've never seen that before, you should be like, what? What? Why? Why square root? Why 2 pi? Why? There's no circles in this thing, in this mass and spring system. Is it because these hoops are circular? No, none of that. We need a reason, a systematic approach that's going to take us from our intuition that, yeah, if we know our spring constant and our mass, we should be able to predict the motion, and specifically we should be able to predict properties like the period, and we don't know how to do that yet. So we know how it should work physically. There is literally one force at play here, the spring force, and yet we still have no obvious way to predict critical features, like the period, size of the oscillations, a bunch of other things, but period's an obvious one to get at. So we need some more tools, and that's what we're going to spend the next several lectures on.